We're next going to move into the area of parallelograms, triangles, and rhombuses. Before we move on, there were two examples above the section that I'm about to highlight, which is what we're moving into next. There was two examples that I did not get through, and these were on a square. So if you were given that the side of a square is equal to 7 centimeters, what's the area of square EFGH? It was defined in the page above. So if we know what the side length is, we should all know that we can square the side to get 49 centimeters squared is the area of that square. Sometimes you're given the area, like you are in 9, is 64. And so if you were solving for each side length, again, to undo the squaring, you would square root. So the side length is equal to 8, in this case, inches. And then from there, just be comfortable with either solving for the side length or for the area of a square. Now, the area of a parallelogram we had discussed on the previous page was base times height. So as we're looking at this picture here, just remember that the base is defined as one, for example, DC or AB. It is the horizontal, and from one of the vertex that you see, either A or C, you would drop a perpendicular down to determine what the height is, or the altitude. So this is height or altitude, and we would calculate it using base times height. Now moving forward, area of a triangle we all know is 1/2 base times height. So as we're moving through this, I'm going to go ahead and trace out in pink. That's the parallelogram formula. This is the formula for a triangle that you see under theorem 11-3. It's 1/2 base times height. And that comes from the fact that, let's say you're looking at that triangle over on the right, FEG. You can see that if I were to build a parallelogram around it, that if I create a triangle on top that is congruent to the triangle that you see FEG, that what I've done is I've built a parallelogram. And so this figure of a triangle is exactly half of a parallelogram. So therefore 1/2 base times height is where the formula comes from for a triangle. Now a rhombus you might or might not be familiar with, so we're going to build it from our knowledge of the area of a triangle. So when we're looking at the rhombus over on the left, keep in mind that you have two diagonals that form 90-degree angles in the middle, and that HJ, let's call HJ diagonal 1 and KI diagonal 2. So I would therefore then define, for example, HJ is D1, so therefore half the diagonals of a rhombus bisect each other. So this is half of D1, or D1 over 2. I can do the same thing over on the other diagonal and define this as half of D2. Now if I look at my diagram and picture this as 4 congruent right triangles, I can find my area of each one of those triangles and then multiply by 4. So for example, where you see they're asking you to find the area of each triangle, what I can do is take the area of one triangle being 1/2 base times height. So the base of, let's say, this triangle right here is this length, which is D2 over 2. So second diagonal divided by 2. And then the height of that triangle would be D1 over 2. Now if we multiply across, because we have fractions here, we have D1 times D2 over 2 times 2 times 2 is 8. So an eighth D1 D2. Now if I wanted the area of the rhombus, I see that I have 1, 2, 3, 4 congruent triangles. So what I would do is the area of the rhombus would be equivalent to me taking what I just found for one triangle and multiplying that by 4, because there's 4 triangles. Now the 4 is going to reduce with the 8 to to get 2 at the bottom or in the denominator. So the formula that I end up with for the area of a rhombus is down below there, 1/2 times d1 times d2. So once again, I'll box the formula in pink here, half d1 times d2. Now the other important formula, which I was just discussing with an AP Calc student, did you guys go over this in geometry? And one of my students who I had prior to calculus, who was in my geometry class last year, he was like, yeah, we did go over it. So I did want to go over this with you guys, where the formula comes from that you see down here, because this is specific to only equilateral triangles, and it comes from our definition of what we know about 30, 60, 90 triangles, as well as the area of a triangle. So let's start with that. So we know that all triangles, it works to where if I take half base times height, I get the area. So now in this figure, we have that if I drop an altitude down, we've done a few problems now that it creates a 30, 60, 90 triangle, or two 30, 60, 90 triangles. So if the side length of the entire base is S, I would define this length that I just drew a brace for as S over 2. So in other words, I'll trace it out for you guys. This is S over 2. And the height, and you'll notice that S over 2 is across from 30 degrees. So if I want the height or the altitude, I would take the short leg and times it by radical 3. So in doing so, it's S over 2 times radical 3. So I'm going to put the radical 3 on top. Now, if I go on to complete this problem and plug everything in, my base is the entire base of the equilateral triangle, which is defined as S. So 1/2 S, and then times the height, which again is S radical 3 over 2. And if I multiply everything out, I get that on top, my numerator has S times S, which is S squared, rad 3 times 1, which is radical 3, and then 2 times 2, which is 4 as the denominator. So the area of equilateral triangle, if I'm given the side length, is side squared times rad 3 over 4. So let's do a few problems here. We have a figure here, which is going to be important that you guys start to notice. Things like 45, 45, 90 triangles and 30, 60, 90 triangles start to emerge to help us find the area of different things like parallelograms and the area of a rhombus. So for example, in this figure that you guys see below here, you're given that this side length here is 2, that this is 10, and so we for sure know that the base is the sum of 2 plus 10. So let's go ahead and write that out. The base is equal to 12. Now, if I wanted to figure out what the height is, I recognize that this is a 30, 60, 90 triangle in which I have, and I know that because that this base angle here is 60, this is 90, so therefore the top angle must be 30. And it looks like I have enough information to conclude that the short leg of that rectangle is, or of that triangle is 2, and then therefore the long leg would be 2 times radical 3. And that gets me what the height is of that parallelogram. So plugging everything in, the area of a parallelogram is base times height, or 12 times 2 radical 3. Simplify that out, that gives me 24 radical 3. Let's go ahead and try it for the next one. If I see that the base of the top is 9, I can conclude that the base of the bottom of that parallelogram is also equivalent, that this is also 9. And if I know that the triangle not drawn to scale here, when I drop the altitude down, that it creates a 45, 45, 90 triangle. And looking at that 45, 45, 90 triangle, I have here that the hypotenuse of that is 6. So going backwards from hypotenuse to leg, I'm dividing by radical 2. So 6 over rad 2, which we can simplify by multiplying top and bottom by rad 2. We get 6 rad 2 over 2, or in other words, when I reduce the 6 and the 2, I get 3 radical 2. And so if this side length is 3 radical 2 and this is a 45, 45, 90 triangle, I can also conclude that the height or the altitude is also going to be 3 rad 2. Now plugging everything in, the area is equal to base times height. And I know my base is 9, my height is 3 radical 2. Multiplying that together, I get 27 radical 2. 3, for the next example, number 3, you see a triangle, you have the base of the triangle, you have the height. Again, the height is the altitude dropped down from a vertex is 12. So the area of any triangle is 1/2 base times height. So we can plug everything in and go ahead and finish off the problem. When you're taking a half of 12, that's going to be 6, and then you take the 6 and you times the 46. So that's going to be 6 times 46, which simplifies down to 276. The last few problems on the next page, we're going to end with number 4. We have an equilateral triangle, and it looks like it defines here that this side length is 8. So therefore the area is radical 3 over 4s squared. So I'm going to write that out as radical 3 over 4, plug the 8 in. 8 squared is 64. So we got rad 3 over 4 times 64. 4 goes into 64 16 times, and therefore that area is 16 radical 3. I'd like for you guys to take a look at 5, 6, and 7 and try to complete that on your own. It wants you to find the area of the rhombus using the fact that AC, one of the diagonals is 20, the other one is 15, and they want you to show that there's more than one way to solve this problem. So fill in the blank to come up with what you think those values are, and we'll double check our answers at the start of Monday's class.